Okay, so this week we are going to wrap up two more non-ideal effects in PN junction diode, which are the series resistance and high-level injection. So before moving forward, let's briefly review what we had learned last week. So going back to the first page of this lecture note, the main topic of this lecture note is the deviations from the ideal current voltage characteristic plot of PN junction diode. So herein, I guess this slide is better to holistically look at what would be happened in non-ideal PN junction diode. So on the left hand side, you can see that the forward biased current versus voltage plot. Of course, the y-axis is converted into the logarithmic scale. So you can clearly see that you see here, this part, the slope is following the Q over KT, which means this part is perfectly well matched to the ideal diode equation. However, as small forward bias regime, the slope is slightly tilted by, in the end, it turned out that the slope of the IV characteristic as small forward bias regime is a Q over 2 times KT, which is non-identical to the slope to be observed in ideal IV characteristics. So that we have learned that where this additional current comes from. As you know, as we have learned and reviewed, the recombination current is the main root cause for this current difference. Okay, and today we are gonna learn why the current versus voltage characteristic plot has been not following the ideal IV characteristic anymore at high forward bias regime. So before moving forward, let's briefly review what we have learned in the reverse bias, the current versus voltage plot as well. So in ideal diode curve said that the current should be saturated once PN junction diode is reversely biased. However, herein, additional current component can be observed. Where does it come from? Yes, it comes from the generation current happened in the depletion layer in PN junction diode. And one another non-ideal event happened in reverse biased current voltage characteristic plot is breakdown. So if reverse biased voltage is beyond the breakdown voltage, then avalanche breakdown, or if PN junction diode is heavily doped on both sides, then tunneling breakdown mechanism would be dominant rather than avalanche breakdown. So this exponentially increasing current can be observed at reverse bias point beyond the VBR breakdown voltage. Okay, so we have understood these physical events, that physical events, and this one. Now the things left behind is this. How come the exponentially increasing current cannot be expected anymore at very high forward bias regime? So to explain that non-ideal factors, we should take into account how much series resistance uh, should be taken into account when analyzing current versus voltage characteristic across PN junction diode. So on the left hand side, you can see that the applied voltage on the x-axis and measured current in the logarithmic scale on y-axis. So if this diode is really ideal, then this dotted line would be expected. However, in real, the measured IV characteristic curve becomes less sloppy at high voltage, high forward bias regime. So suppose that are you have, see this. you have applied say 0.8 volt and you have expected 1 milliamp. However, to obtain 1 milliamp current across PN junction diode, actually you should apply 1.2 volt. So how come 0.4 volt is more necessary to achieve 1 milliamp current? The ideal diode equation said you need 0.8 volt to achieve 1 milliamp. However, in real, you need to apply 1.2 volt to obtain 1 milliamp. Why is that? How come this voltage loss has been happened? So going back to this cross-sectional view of PN junction diode on the upper side, once you apply a certain amount of voltage across PN diode, you may expect a certain amount of current across PN diode. And herein, the quasi-neutral region on the P side as well as in the N side, there is very small tiny amount of resistance value because this is not superconducting material. It is semiconducting material so that it has its own unique resistance value. So as we have learned, you may estimate quantitatively the resistivity of on the P side as well as N side. So resistivity is inversely proportional to the conductivity, and this conductivity consists of many terms: unit charge, mobility, electron concentration, plus unit charge, mobility of hole, and hole concentration. Because this part is a p side, so electron concentration is much smaller than hole concentration, so you can ignore this term. Then the resistivity on the p side becomes 1 over q mu p, and this p would be determined from acceptor concentration, net acceptor concentration in p side. If there is a small amount of donors included in the p side, then you should take into account the Na minus Nd as a net doping concentration. Okay, so you can repeat these steps for quasi-neutral region in the N side as well. Then you may confirm that this value should never be 0. So there is non-zero resistivity, and depending on the physical dimension of quasi-neutral region in p side and n side, say the cross-sectional area is A and the length is L, I would say, L p side. The reason why I didn't use the LP, because this LP indicates the diffusion length of hole in p side, right? So that would make you confused a lot. So I would like to say LP side. Okay, then the resistance value in the p side would be resistivity on the p side times LP side divided by cross-sectional area, and this value should never become 0. So once very high current is flowing across this p side quasi-neutral region, then I times R p side would become the delta V, a certain amount of voltage drop. Okay, so delta V in the p side, and you can repeat these uh, steps for n side quasi-neutral region as well. Then you're gonna get the delta V n side. And now let's sum them up. I mean, the delta V, total delta V is delta V p side plus delta V n side. And this delta V is corresponding to this 0.4 volt. Okay, so if your PN junction diode is really perfect and ideal, then this delta V value should be 0. However, the quasi-neutral region in p side and n side, the resistivity value in those regions should never be 0. So we shouldn't assume the 0 resistance in the quasi-neutral region. So this impact becomes more significant when the current across PN diode becomes increasing and increasing. That's the reason why we are talking about this impact of series resistance at high forward bias regime rather than, small forward bias regime. Okay. All right. Then how to extract out experimentally the series connected resistance value coming from the p side quasi neutral region and n side quasi neutral region. How to do that? So let me erase all my notes first. Okay, here, so this solid line indicates a measured data, and the dotted line indicates I comes from or obtained based on the ideal diode equation. And at high forward bias regime here, so you're gonna estimate for given current value, say I1, I2, and I3, you may get delta V3, that is delta V2, that is delta V1. And convert, you can rearrange those values, I mean the current value versus delta V value. So here on y-axis, I put the delta V values. On x-axis, I have put current value. Then you're gonna get this straight line. So the slope of this delta V versus I indicates a total series resistance coming from the P side and N side. Okay, and experimentally you may extract out the RS value, and theoretically you may estimate and calculate the RS P side and RS N side, as I have told you. If once you know the physical dimension of the PN junction diode, and once you know the doping concentration on the P side and N side, then you may theoretically estimate the RSP side and RSN side and sum them up. Then it should be uh, identical, equal to the experimentally observed and measured RS value coming from this delta V versus I plot. Okay, all right. And the second reason why we may see we may not see the exponentially increasing current in PN junction diode at very high forward bias regime is high level injection effect. So basically, when we are deriving the ideal diode equation, we have assumed that the low level injection, I mean, from P side to N side, the holes are injected into the N side and it becomes minority carriers and is going to diffuse toward the opposite side of the N side, away from the depletion region. So basically, we have assumed that the total amount of injected holes into the N side should be much, much smaller than the majority carrier concentration in N side, which is electron concentration in N side. But if you apply super high externally applied bias across PN diode, I mean, as denoted here in this lecture note, if where's my note? Yeah, as VA increase more and more, the side of the junction, which is more lightly, I mean, the lightly doped side one, will eventually reach to the high level injection. So herein, for example, if you have a P plus N PN junction diode, then in the N side, I mean, because P side is heavily doped, right? So more holes would be diffused into the N side, injected into the N side. So tons of holes would make some critical impact on the majority carrier concentration in N side. So here the in N side at thermal equilibrium, in N side electron concentration, which is the majority carrier concentration, should be affected significantly because of the injected holes coming from the P side into the N, because P side is now heavily doped. So at non-thermal equilibrium state, in N side, electron concentration is higher than N sub N naught. So going back to the basic assumption of low-level injection, I said the majority carrier concentration has not been significantly affected because of the injected carriers, but the minority carriers concentration are significantly affected because of the injected carriers. So that is a basic concept of low level injection. But now herein, the high level injection. the majority carrier concentration would also be affected significantly. So that's the reason why here, uh, for example, in P plus N junction, the lightly opposite one has more uh, vulnerable to the high, injected carriers. Okay, all right. So on the second line, there is another example, N plus P junction, then definitely more electrons would be injected into the P side, which is the lightly opposite one in this N plus P junction. And at thermal equilibrium in the P side, the whole concentration, which is the majority carrier concentration in N plus P junction, and at non-thermal equilibrium state, the whole concentration in the P side would be higher than the PP naught, which means that majority carrier concentrations are significantly affected because of the injected carriers. Okay, so this physical event would induce a very significant gradient in majority carrier profile. I guess, do we have any profile? No. So let me draw the carrier profile plot here. Okay, this is P side and that is N side. So I said P plus N diode we got, and more holes would be injected into the N side. So I say that is hole concentration in the N side at thermal equilibrium. That is electron concentration in the N side at thermal equilibrium. And if low level injection is dominant, and this N and naught should be equal to NN. So NN, that this line indicates NN, should be identical to the N and naught. But because the holes are now injected into the N side, the P sub N, at non-equilibrium state, the certain amount of externally applied bias has been given across p-n junction diode, then P sub n should be higher than the Pn naught at or near the depletion layer, x of n, 0 minus xp, okay? But this increased, the delta P sub n, right? Delta P sub n is defined as Pn minus Pn naught, right? So this delta Pn, in terms of the magnitude of this delta Pn, or simply speaking, delta Pn never affect this n sub n, because n sub n is way higher than delta Pn. However, more holes are injected more and more, then so this physical event has been induced because of the increased forward bias. Very strong forward bias has been applied. Then we may expect many holes would be injected. The lots of holes would be injected into the N side. Then this delta P sub N would becomes like that. So, and much more forward bias has been applied, then this P sub N profile would becomes like that. And take a look at this part. Now the P sub n is higher than N sub n. That means many electrons in this n-type material would be induced to compensate these injected holes. So if I draw the majority carrier concentration profile, that would be this. Okay. Instead of a straight line, n sub n, previously I used the n sub n once p sub n is higher than n sub n, then the many electrons would be diffused toward the edge of the depletion layer because of compensating these injected holes. So simply speaking, because there are many holes are injected here at x of xn or at the edge of the depletion layer, the electrons, many electrons in the antimaterial would be induced toward the edge of the depletion layer. So if you imagine how much electrons would be living in or existing near the depletion layer edge, I mean the x of xn, then you may expect that there is more electrons, and it it would becomes it would become identical to the n sub n naught at bulk regime of n side. So this part, this doping concentration gradient would be happened. So here significant gradient in majority carrier profile. I'm talking about this part. Yeah, this part would be obtained. So once the majority carriers are attracted and moved toward the edge of the junction layer, afterwards, those electrons would like to, you know, would like to induce and cause the diffusion current because, you know, doping gradient would definitely make diffusion current. Okay, so the injected holes, let me change my color. Here, many electrons are now accumulated toward the edge of the depletion layer, but in the end, those electrons should be diffused toward the opposite side of the n-side region. So this movement of electrons would cause the diffusion current, i.e. diffusion across p-n diode. But this current direction is opposite of the forward bias current, right? So that is the main reason why majority carrier diffusion current herein would reduce the diode current from the ideal IV characteristic. Okay, so this high level injection effect as well as series resistance effect. So those two events, two things would affect and would block the exponentially increasing current in rear PN junction diode. Okay, all right. So that's all for the deviations from ideal current versus voltage. So you may guess, so where's my mouse? Okay, here. So this is a, oh, my pen. Okay, so herein, I guess let me draw the full IV characteristic in a single shot. Current versus voltage. Okay, so at forward bias regime, the ideal diode current would be exponentially increasing, and in the reverse bias regime, very tiny amount of saturated current would be flowing, whatever, regardless of the magnitude of the reverse bias voltage. But in practical PN junction diode, if you have any chance to measure the real IV characteristic, then you're gonna see this. Okay, so the blue colored one indicates the IV characteristic of real PN junction diode, and red colored IV characteristic indicates the ideal diodes. And herein, how come the current is exponentially increasing? Because of the breakdown. And how come this saturated current would be monotonically increasing? Why is that? Because of the generation current. Okay. And how come as small forward bias regime, some certain additional amount of current has been added up into the ideal diode currents? Why is that? Because the recombination current happened. Okay, and this part has been well matched to the ideal one, and at very strong and full high forward bias regime, the diode becomes a resistor. Why is that? Why the exponentially increasing current can never be achieved at high forward bias regime? Because of the series of resistance, because we should take into account the additional voltage drop happened in quasi-neutral region on both p side and n side, as well as high level injection. So additional majority carrier concentration gradient would be induced, which would result in the oppositely directed uh, current happened. So that would cancel out the forward bias current. So HLI, high level injection, and series of resistance RS, those two things would be combined together to block the exponentially increasing current across PN diode. Okay, so I hope you to fully explain the comparison between ideal IV characteristic one and real practical IV characteristic. And you should draw the energy band diagram if necessary to explain the physical events and physical origin of this difference happened in ideal IV versus real IV. Okay, and this PN junction diode theory would be the base or basics or a good starting point to understand bipolar junction transistor as well as MOSFET. Okay, so if you have some time, please review what we have learned up until now. And we have done the DC analysis as well as electrostatic analysis. So please review all the stuff and see you in the next movie clip. So in the next movie clip, I'm going to tell you some derivation of narrow base diode current versus voltage characteristics. So this would be the good starting and initial point in understanding the bipolar junction transistor. All right, so let me stop here and I would like to see you in the next movie clip. Thanks for your attention and see you in the next movie clip. Bye bye.